Welcome back. In this video, we're going to be talking about operations on functions. So taking two functions and adding them or subtracting them or multiplying them together. And we'll also be talking about a special operation, composition of functions. First off, operations on functions, adding them, subtracting them, multiplying them, dividing them, it means exactly what you expect it would mean. So when I say something like, here's a function f and a function g, please find f plus g, I literally do mean just add the two functions together, or f times g, multiply the two functions together. There is a couple little things that we have to talk about, though, which is that if you're taking two functions and combining them together in some way, you'll get another function. And that means that you're going to have to be thinking about the domain of that new function that you're creating and how does it relate to the functions that you built it from. So for the addition, multiplication, and subtraction, if we're just adding, subtracting, or multiplying functions together, then the domain is actually not too hard to find. It basically would be all the values that are in the domain of the first function and at the same time in the domain of the second function. We have an extra quirk when we're talking about division, because in addition to the functions f and g both needing to be defined, so in other words, when we're looking at f divided by g, we need to think about where is the domain of f. We also need to think about where is the domain of g. We also know that g can't be equal to 0, because of course if it is, then that means you'd have something undefined. So in addition to the values that can go in for f and the values can go in for g rather, we also want to restrict our domain so that the values of x that we put in don't make g equal to 0. So in other words, we don't want the original functions to be undefined, and we also don't want our combined functions, the product, the quotient, the difference, the sum, we don't want that to be undefined either. So just a couple of examples here. We've got three functions, f, g, and m, and the first one would be me finding just f minus g, and that one's relatively straightforward. So when I write this, when I write f minus g of x, that's the function I get when I take f of x and I subtract g of x from it. So let's do that. F of x is 6x minus 1. And g of x is x squared minus 5x plus 6. And now we'll just subtract away. We'll have negative x squared. We'll have 6x minus negative 5x, or 6x plus 5x, that's 11x. And then for the final part, we have negative 1 minus 6. That would give me negative 7. So there we go. There's our function, f minus g. And as far as the domain goes, f is defined for all real numbers. Remember that when we're thinking about domains, there's really right now only two kinds of restrictions to think about. If we've got something that's a fraction, we don't want the denominator to be 0, and if we have roots, we want the inside to be 0 or larger. And for this, there is no root, there is no denominator, so for this, any value of x would be fine. And similarly, g of x, that's a nice little polynomial. That's defined for all values of x. So that means f minus g should be defined for all values of x as well. So for the domain, I'll express this in interval notation, the interval from far left to far right. Or you could say that x is an element of the real numbers. That's a different way that you'll see in some books. This means exactly the same thing, that any real number will be a valid number to put in for x. So the fancy little r, this is the symbol that we use for the set of real numbers. And the sort of funny looking E, that's actually the Greek letter epsilon, and then we use that to mean is an element of. So if I were reading this, I would read this as x is an element of the real numbers. In other words, we're saying that x can be anything from positive infinity to negative infinity. All right, let's do another one. The next one we're looking for is g times m, and g of x times m of x. G of x is that first polynomial, and m of x, that's that nice little quotient. As I'm writing m of x down, I'm thinking ahead of myself that I'm probably going to want to factor it. I'm also going to want to factor g, because I'm thinking about maybe some things might cancel. So I'll do that on the next step. So g of x, x squared minus 5x plus 6, that does factor out rather nicely. X minus 2, x minus 3. And m of x, the denominator factors out rather nicely as well. We've got the denominator factors as x minus 2, x plus 2. And then we can see that the x minus 2's will cancel. So what we'll be left with, we'll have x minus 3 times x minus 3 in the numerator, or x minus 3 squared. And then in the denominator, we'll just have x plus 2. Now, again, when we're thinking about the domain, we're thinking about all the values of x that are inside of the first function and also at the same time inside the second function. So the first function, g of x, that was our nice little polynomial. That's defined for all real values. That's good for any x that we feel like putting in. But if we're thinking about g of x, the second function, m of x, that had two excluded values. X could not be 2 and x could not be negative 2. Now I know what some people might be thinking right now, that 2 might be okay to use because we've canceled out the x minus 2's in the top and in the bottom. Unfortunately, just canceling those terms out doesn't fix our problem, because remember, this new function that we built here was made out of g times m, and if you went back to the beginning and tried to put in 2 for x, this second expression here on the right, this x minus 3 over x squared minus 4, that would be undefined, so you wouldn't be able to cancel things out and simplify things out. So again, the moral of the story here is that when we're thinking about domains, it's not how does the final result look like. So we're not just going to look at the final result and say, oh, x can't be negative 2. We have to look at the function that we began with. And the functions that we began with, the first one's defined for all real values. The second one is only defined for values that are not positive 2 or negative 2. So that means in my domain, positive 2 and negative 2 both have to be excluded. So I'm going to write this using set notation. So rather than using interval notation, because that will be probably a little bit messier, when you're just excluding one or two values, set notation might be the faster way to go. We'll say it's the set of all x's such that, again, that vertical line that I write means such that, or with the property that, and then I can list all the little restrictions afterwards. So the restrictions are x can't be 2, and x cannot be negative 2. And since it's set notation, we are putting those in curly brackets, or my best attempt at drawing curly brackets, which I can never quite get to look convincing. Oh well. So there we go. There's our function. G times m simplifies out to give me x minus 3 squared all over x plus 2. And there are two values that are excluded from its domain, positive 2 and negative 2. Okay, one more. This is now looking at the quotient, g divided by m. And so if we're thinking about the quotient, we need to think about the domain as the values of x that are good for the numerator, the values of x that are good for the denominator, and also exclude any value of x that makes the denominator 0. So we're going to actually have to think about not just where g and m are defined, but also where is m potentially equal to 0, and that value would have to be excluded as well. So just to start off, we'll write down what we have. G of x, that's that polynomial. And m of x, that was that little quotient that we had. So this is one thing divided by a fraction, and if we're dividing by a fraction, that's the same thing as flipping and multiplying by the fraction. So we will say that this is the same thing as taking g, and instead of dividing it by m, we'll flip m and multiply it. And now let's simplify this. The polynomial that I have on the left factors just as it did before, as x minus 2, x minus 3. And that the polynomial here, the x squared minus 4, that factors as x minus 2, x plus 2. And then we can cancel some things out. We can cancel the x minus 3's. And that leaves me with x minus 2 times x minus 2 times x plus 2. We'll have x minus 2 squared, and we've got x plus 2. Okay, so far so good. We now have to think about the domain. And for that, again, we're thinking about all the values of x that are inside the domain of g, that are in the domain of m, and also we want to exclude any values of x that would make this, which is the denominator here, equal to 0. So as far as the things that are in the domain of g and in the domain of m, we know that for g, this little polynomial we have here, that's defined for all real numbers. So its domain is everything. But we know that m has two excluded values. X cannot be 2, x cannot be negative 2, otherwise m is undefined. Also, if we're looking here, if you were to let x be 3, then the numerator would be 0, which would make the entire thing 0. In other words, you would now be dividing by 0. So, as it turns out, there are 3 values of x that we need to exclude for this. So, for our domain, we can say that x cannot be 2, and x cannot be negative 2, and that's because those would both make m undefined, so you would have g divided by something that's undefined. Not good. And the other value that we have to exclude, oh, lost my negative there, positive 2 or negative 2, there we go. The other value that we have to exclude is the value of 3. And the reason that we're excluding a value of 3 is because if x were 3, that would make x minus 3 0, which would make all of m 0, which would mean you'd be dividing by 0, and of course that is undefined. So 3 values of x here that we're excluding from our domain. So for when we're looking at quotients of two functions, again, we're looking for where the functions are both defined and also where the denominator is not 0. So both functions are defined when x is not 2 or negative 2, and the denominator is not 0 provided that x is not 3. All right, so a new operation to introduce here, the idea of function composition, and the little motivating example I have here is this. This is true, I looked this up for the density of salt. For table salt, its density is 2.17 grams for every centimeter cubed. So I created myself a nice little function here that if you wanted to know the weight of an amount of salt, and if you happen to know its volume, then the weight of your salt would just be 217 times whatever the volume of your salt is. Now, if we're thinking about our salt being shaped like a cube, so we've got a cube of salt and the side lengths are x centimeters, what I'd like to now come up with is a function w of x. In other words, the original function took volume as an input and gave me the weight of salt as its output. Here I want a new function that takes the side length of my little cube of salt as its input and gives me the weight of salt as its output. So let's just start off with this. We know that if W of V is 217 times V, so in other words, since we've got this function, we have a relationship between weight and volume. Also, fun fact that we know, this is a cube of salt, so that means the volume of that cube should just be the side length cubed. Remember that for a cube, where all the side lengths are all equal to each other, the volume is length times width times height, and all of those are just x. So that means the volume of my cube of salt should just be x cubed. So then the next thing that I need to do is ask myself this: how do I put these together so now I've got a function that's just strictly in terms of volume and, just in terms of weight and x. So here we've got a relationship between weight and volume. Now we've got a relationship between volume and x. And so my plan here is what I'm going to do is take volume in this equation and replace it with what volume is equal to, x cubed. So if I were to do that, so by combining these two together, or in other words, putting one function inside of another one, I would get that the weight should be 2.17 times x cubed. This is now giving me something where if you give me an input value of x, a side length, I'll get an output value of w. I'll get an output value of weight. So that means that we've got our function, w of x is 2.17 times x cubed. There we go. We've composed two functions. We've put one function inside of another. Okay, and I'll just finish off the last little part here, which is the weight of the cube of salt whose side length is 5 centimeters. And that's easy enough for me to do now, because if you're looking for that, you just want to know what is the weight of a cube of salt whose side length is 5, and that would be 2.17 times 5 cubed, or 271.25. So you could say that the weight is 271.25 grams. There we go. So we tackled function composition here through this story, through taking one function, putting it inside another to get a new function. And that's kind of the idea that we're going to be talking about extensively, actually, when we get into the next section and talk about graphing via transformations. Those we can actually explain in terms of doing one function after another, or putting one function inside of another. So let's take a look. So our definition that we're going to give here for composition of functions, or also our notation for it, is this, the little circle. When you see this little circle, this is the function composition operation. I would read this as f composed with g. In other words, when you're saying f composed with g, you're talking about putting one function inside of another, that g is being put inside of f of x. Just like how we did in the previous example, where we took the volume function and we put it inside the weight function. So we could think of this as taking weight composed with volume, that we put the volume function inside the weight function. So that's our idea, that if we're looking at composing two functions, what we're talking about is putting the one function inside the other, that f composed with g is just taking g of x and putting it inside of f of x. Domains are a little bit weird here as far as the things that we'll need to think about. Firstly, you want to make sure that the thing that you're putting inside is defined. So in other words, all the x's that you're putting in have to certainly be in the domain of g. Otherwise, you wouldn't be able to find out what f of that is. If g was undefined, then how would you find f composed with g? The second thing is, you need that those values of x that you get coming out of your function g, in other words, you need to know that the things that are being put inside of f are also defined. So you need, for the domain of f composed with g, all the x's that make g defined, and at the same time all the x's that where g of x can go into f and have it be defined. We're going to see some discussion about domains in a little while, but right now, this example, I just want us to mechanically try out finding f composed with g evaluated at 2. So here we've got two functions, f and g. They're both nice little polynomials. And if you're looking at f composed with g of 2, that's saying you want f of g of 2. So our first plan is, and for these sorts of things, for function composition, we work our way from the inside out. First, I'll find out what g of 2 is, and once I know what that is, then I can find out what f of whatever that value is. So what I'll do first is g of 2, and for g of 2, I do that just by putting in 2 for x. So let's see, g of 2 would be 2 times 2 minus 1, which if we simplify that, that would be 4 minus 1, or 3. So then g of 2 is 3. So good. So now we know what the inside part is. This is equal to 3. Now we need to use that to find out what is f of that value. What's f of 3? And we do that just by putting in 3 for x in our function f of x. So putting in 3 for x, and we'll get 9 plus another 9, or we'll get 18. Just one little thing that I wanted to do here, kind of as an aside. If you're thinking back to when we first started talking in chapter 3.1 about relations and how you could describe them as a mapping, kind of what's going on here is, if you're thinking about the domain for g, that it's taking the value of 2 and mapping it to the value of 3. That's what g of x is doing. And then f of x picks up from that point and carries onwards and takes that value of 3 and maps it to a value of 18. So we're basically just doing one function after another. That when we put 2 into the input of g, it gives us the output of 3. And when we put that as the input for f, it gives us the output of 18. All right, so now here we're going to find some compositions of two functions, and we're also going to think about their domain. So starting with the first one, f composed with g. So this would be f of g of x. And here we're dealing with things symbolically rather than numerically. We're not actually going to be putting in a value for x. That means that g of x is just the same thing as square root of x. So this would be f of square root of x. And if you're having fun flashbacks to when we first introduced this idea of evaluating a function back in 3.1, we're doing exactly the same thing here. We want f of square root of x, which means we'll take this function and we'll replace the x's with square root of x's. So the original function for f was x squared minus 4, and we're replacing the x's with square roots, so we'll have square root of x squared minus 4. And that just simplifies down to give me x minus 4. Some things just to think about as far as the domain goes. Firstly, remember that for our domain, we need all the places where our inside function is defined. Because remember that at the beginning of this, we started off by putting g of x inside of f. So in other words, we need this g of x to be defined. And that's only a real number if x is 0 or larger. So already, just from this, we know that x has to be 0 or larger. We're not dealing with negative values for x. So if we're thinking about where we ended up, does this define for any values of x that we have to restrict? Are there any things that we have to think about x minus 4? And the answer is, well, no, x minus 4, that's defined everywhere, so we're good there. So putting the two things together, the final result is defined for all real numbers, and the input, to make that defined, that root of x defined and real, we need it to be 0 or larger. So altogether, that means we need to have that x is 0 or larger. So for my domain, for this, x needs to be 0 or larger. I'll use interval notation here. That makes the most sense. I'll say that x is 0 or larger, including the 0, so square brackets around that. And you can quickly check. I mean, if you were to try to use a negative value for x, if you used a value of x of -1, you'd be stuck right at the very first line. You'd be finding square root of -1, and that's undefined, so you wouldn't be able to find this, which means you wouldn't be able to find the final result. And so that's one further confirmation for us how I know this domain is 0 or larger. Let's do the reverse. For part B here, we want g composed with f, so we want to put f of x inside of g, or in other words, we want to put x squared minus 4 inside of g. And if we put that inside of g, that's replacing the x that's here with x squared minus 4. And that's easy enough to do. That would be then square root of x squared minus 4. Now, if we're thinking about how we found our domain, we had to ask ourselves for part A, where is the input for the function f? Where is that defined? Where's our final result defined? What do they have in common? So we'll do a similar sort of thing here. The inside function, where is it defined? That's defined for all real numbers. What about the final result? Where is this defined? Well, that's a square root, so you would need x squared minus 4 to be greater than or equal to 0. Or in other words, you would need x squared to be 4 or larger. And you can figure out for yourself. We haven't talked yet about solving inequalities where there are squares, but this is an easy enough one for us to reason our way through. We know that if x were 2 or larger and you squared it, you would get a number that's 4 or larger. And also, if you knew that x was -2 or smaller, so -2, -3, -4, all those numbers, when you square them, you get something that's 4 or larger. So for this, x cannot be anything in between. If you are between -2 and +2, then the inside of your square root is going to be a negative, and that's too bad for you. That means you're not going to be getting a real number outside of your function. So as far as our domain goes, the domain is that x has to be either less than or equal to -2, or it's going to be 2 or larger. And so remember that the symbol that we're using here, this union symbol that we use when we're connecting two or more intervals. So we have all the values up to and including -2 together with all the values that are 2 or larger. And now we're pretty much good to go. A couple of things just to notice about this. First part, the obvious one, which is, and I have here the note at the bottom, that f composed with g and g composed with f are usually not the same thing. And that's very much true here. If we compare f composed with g and g composed with f, these are absolutely not the same function. And furthermore, the other thing that's quite true is that they don't even have the same domain. That the domain for f composed with g is all the non-negative numbers, whereas g composed with f includes some negative numbers, lots of them. So for example, if you were to think about the value of x being 1, 1 would be fine for f composed with g. You could totally put in a 1 for x here, find out what the square root of 1 is, then put it into f and get a value coming out. On the other hand, if you tried to put a 1 in here, so far so good, you'd have 1 squared minus 4, which is negative 3. But then once you put that in a square root, you'd have square root of negative 3, and that's not a real number. So not only is f composed with g and g composed with f, not only do they often look different, often they don't even have the same domain. So the one little thing that I sort of toyed with at the very beginning when I introduced the example with the salt and the volume, if you're remembering back to there, we had a function for weight and we had a function for volume, and that I said we were essentially putting the volume function inside the weight function. We were finding volume composed with weight. That's usually how we think about things when we're thinking about composition of functions. That if you're thinking about something like f composed with g, you're thinking about it as g being put inside of f, that g is the inside function and f is the outside function. And actually, for complicated looking functions, ones that there's no more than one operation going on, something like this, you could break that down and think about it as a composition of functions. If you're thinking about just this function a of x, which is square root of x plus 1, if you were thinking about what happens to the value of x when you put this into this function, if you're thinking the order that the operations would go in, if you actually had a number for x and wanted to calculate this, you would first need to figure out what x plus 1 is. So your first operation would be the adding 1 function. And then once you figured out what x plus 1 is, then you would take care of square rooting. You would deal with the square rooting function. So really, you could think of this as taking the x plus 1 function and putting it inside a square rooting function. So you could say that you could rewrite this function as f composed with g, where g, the inside function, is x plus 1, and f, the outside function, is square root of x. And in fact, you can confirm that this is correct. If you were to take this and just check out what is f composed with g, you would see that this would be f of x plus 1. In other words, putting g of x inside of f. And since f is the square rooting function, we are putting x plus 1 inside the square rooting function. And then lo and behold, yes, that's exactly the function that we started with. And so that's something that we can do here with any two functions with any function that we have, we can break them down into two or more functions, so that the composition gives us the original function back. And again, the way that I try to think about this is, just like I did for this, imagine you had a number to put in for x. What would be done to that value of x in what order? So for this square root of x plus 1, first you'd add 1, then you would do the square rooting after. And if I'm thinking about this function p of x, if you put in a number for x, if you were thinking about what gets done to that value of x, the first thing that happens is the subtracting 1 happens to it. You'd first find out what x minus 1 is. You'd deal with what's inside the bracket. And then you would deal with the power of 4 next. You would raise it to the power of 4 as your second move. You would deal with exponents next. And then last thing that you would deal with would be the addition, the adding 2. So we really actually have three functions that are going on here. It's not just two functions. We have three choices of what our functions are. So I've written them in order from first to second operation to third. So if we're thinking about inside functions versus outside functions, the inside function is what you do first, the outside function is what you do last. So suppose I were to take my inside function as just being the subtracting 1 function. So I could take g of x being just the function that subtracts 1. And then for my outside function, I'll take everyone else, the function that raises things to the power of 4 and then adds 2. And if I were taking that verbal description and writing it out as a function, it's the function that takes your input, raises it to the power of 4, then adds 2. And now, if we want to, we can quickly confirm for ourselves that f composed with g does give us our original function. So let's check that out. F composed with g of x, or in other words, f of g of x, which is f of x minus 1. G of x is x minus 1, and f of that would be replacing this x with x minus 1. So for f of x minus 1, we would get x minus 1 to the power of 4 plus 2. Since f takes its input, raises it to the power of 4, then adds 2, if x minus 1 is the input, then that x minus 1 will get raised to the power of 4 and have 2 added onto it. And so we can see that if you're looking at f composed with g, you do get the original function p of x back, that this is exactly what the function is that we wanted to start with. Now, I did say that that was one option, and I'm going to just give myself some more room here. So this was one of the options that we have if we're thinking about expressing p of x as a composition of two functions. So that's one choice. I'll put in an or here. Again, thinking about our operations, for this function x minus 1 to the power of 4 plus 2, the operations were subtracting 1, then raising things to a power of 4, then adding 2. We did our functions g and x by having g first just doing the subtracting 1 and f doing everything else. We could also do maybe g does the first two things and f does the last thing. So you could say maybe g of x does the subtracting 1 and raising that to a power of 4, and then f of x, the outside function, will just do that last step, the adding 2, so taking its input and adding 2. And you should quickly confirm here that f composed with g also gives you your original function back. F composed with g would be f of x minus 1 to the 4, that's g of x, and f takes that input and adds 2 to it, so f of x minus 1 to the 4 would be x minus 1 to the 4 plus 2, which is again your original function p of x. So once again, we have multiple ways that we could do the same problem. Here you have two choices for what you could write as your inside function and your outside function if you were trying to express p of x as an inside function that's been put into an outside function. Let's do one more. So here for this one, I'm going to again think about what are the operations that are being done here. So the input-output idea here is if you were taking a value of x as your input, the first thing that you would have to do is figure out x minus 3. What is that? So your first function is the subtracting 3 function. Once you've subtracted 3 from x, you need that x minus 3 to be in the denominator. In other words, you need to take whatever that output is and take the reciprocal of it. So the next function after subtracting 3 is the reciprocal function. And then once you have the x minus 3 now in the denominator, you need the numerator to be 4. And you would do that by multiplying that function by 4. So the next operation is take what you've got and multiply it by 4. And so if we're thinking about splitting this up into an inside function g and an outside function f, you have, again, two choices. Your inside function could be the subtracting 3, and the outside function could be take the reciprocal, then multiply by 4. So you could say that the inside function is subtracting 3, and that the outside function takes the input and takes the reciprocal of it, and then multiplies that by 4. And you should check to see And I'm not going to do this right here, but you can check to see that f composed with g is indeed equal to this function q of x. And it does. If you were to take g of x and put that inside of f of x, f composed with g would be f composed with x minus 3, which would replace the x in f of x with x minus 3. So yes, we can confirm, and I'll let you do that as an exercise, we can confirm that yes, indeed, these two functions would work for a way of decomposing q of x into two simpler functions. You could also say that the inside function, maybe that would be the reciprocal and subtracting 3, and that the outside function would just be the multiplying by 4. So the inside function could be that you subtracted 3 and then took reciprocal, and then the outside function is that you multiplied by 4 of whatever the input is. And you should confirm that that also works as well. One final thing that you can check, and this is, I don't expect us to do that for this example, but if you wanted to, you could. You could also look at doing a composition of a function with another function with another function. If you were to say, well, why don't we just actually split it up into 3 functions? We have the innermost function, and then a middle function, and then the outermost function. So I'm going to call these f, g, and h. H, my innermost function, which is the subtracting 3 function. G of x, the middle function, the next step would be the taking the reciprocal. And then the final step, the final function, would be the multiplying by 4. And you can check to see that if you were to check that f composed with g composed with h, or in other words, taking h of x and putting it inside of g of x, and then putting that inside of f of x, you should get your original function q of x back. That if you actually thought of taking this as a composition of 3 functions, that we would take this and put it inside of this and put that inside of that. So h goes inside of g, which then goes inside of f. You can confirm that this also would get you your original function q of x, so that you actually have 3 options for how you could take this function and decompose it. And actually, for the previous example, you also had 3 options. We could have done a similar thing there. I just wanted to do one little example where maybe I decomposed it with 3 functions rather than 2. And now, last little thing that I want us to do, and this is the last example, which is going to lead us to a future topic, which is looking at composing these 2 functions. These 2 functions, we're going to see g and f are kind of special in a sense, because f composed with g just gives us x, and g composed with f also just gives us x. Remember, I said a couple of slides ago that f composed with g and g composed with f, that they're often not the same thing. This is a special kind of relationship between functions. They're f composed with g and g composed with f are both equal to each other, and they're both equal to x. So let's just show that, at least for now. That's all we want to do with this example, show that that's true. So if we were looking at f composed with g of x, or in other words, putting g of x inside of f of x, that would be me putting that cube root of x plus 1 over 3 inside of f. And then, of course, remember that when we're putting this inside of f, we'll be replacing the x in that function with this cube root of x plus 1 over 3. So f, the original function, was 3 times the input value cubed minus 1. And here the input is cube root of x plus 1 over 3. And now we're just going to simplify this. The cube root and the cube cancel each other out. When we have a cube and a cube root, they both cancel. So that means we'll be left with just x plus 1 over 3. And the 3's would cancel, leaving me with x plus 1 minus 1. And then the plus 1 and the minus 1 would cancel, leaving me with just x. So far so good. We've got that f composed with g gives you x. So if you take any x that you can put into the domain of g, and g's domain is all real numbers, if you're wondering what the domain of g is. Since g is a cube root, we don't have to worry about the inside being negative. So x could be positive, x could be negative, doesn't really matter. Any value of x that we can put in for g, for f composed with g, will give us an output of x. I'm going to add an extra sheet here. Because now we're going to do g composed with f. So we've done f composed with g, and we've got that f composed with g has an output of x. Now g composed with f. Or in other words, putting f of x inside of g of x. F of x was that 3x cubed minus 1. And so we'll be taking g of x, and we'll be replacing the x that's in g of x with 3x cubed minus 1. So let's do that now. G of x was originally cube root of x plus 1 whole thing over 3. And we want to replace the x with what f of x is, which was the 3x cubed minus 1. And now I just need to simplify that. Inside that root, in the numerator, the plus 1 and the minus 1 will cancel each other out, leaving me just with 3x cubed over 3. And the 3's cancel each other out, leaving me with just cube root of x cubed. And cube root of x cubed, that's just x. So I want to just sort of dance around why this worked out the way that it did. And I'm going to do that by going back to these functions and thinking about their operations, the operations that make up f and that make up g. If you're thinking about f, the operations that you do inside of f in order, if you were to give me an input value for x, the first thing that you would do here would be to cube it. And then once you've cubed it, you would then multiply it by 3. And then once you've done that, once you've multiplied by 3, you would then subtract 1. So if you're thinking about f is actually made out of 3 functions. F has cubing happening, then the multiplying by 3 happening, then the subtracting 1. If you're thinking about g, it also has a bunch of operations that it's doing if you were thinking about what you would do if you had a value for x. If you put in a value for x into this function, you would first have to add 1. Then once you knew what that numerator is, you would then divide by 3. So the next function is the dividing by 3 function. And then once you knew what the inside of that root is, you would deal with the cube rooting. So your final function would be the cube rooting function. The one thing that I want us to notice here, and we'll talk a lot more about this in a future section, is that these operations that we have for f and for g, they're opposites of each other, and they're being done in the opposite order. X cubed is really the opposite function of cube rooting. You have multiplying by 3 and dividing by 3, those functions are opposites of each other. Subtracting 1 and adding 1, those functions are opposites of each other. So f does cubing, then multiplying by 3, then subtracting 1, and g kind of does the reverse in the reverse order. it adds 1, then divides by 3, then cube roots. So not a huge surprise here that F composed with G and G composed with F both in a sense lead us to the same result. G in a way is undoing everything that F does, and F in a way is undoing everything that G does. But again, we'll talk a lot more about that in a future section.